Importance of groundwater. Groundwater is critical in supplying fresh water to streams and wetlands. The water is used mainly for irrigation, manufacturing, domestic and other purposes. Due to limited availability of surface water, there is an increased dependence on groundwater. Due to its overuse and improper use, the proper use and protection of groundwater require an insight and an understanding of the groundwater system. Out of the total Earth's water, 97% is salt water, which is in the oceans, the remaining 3% being fresh water. Groundwater is a significant part of the hydrological cycle, containing 21% of Earth's fresh water. It makes up about 1% of the water on the Earth. Most water is in oceans and up to 35 times the amount of water is in lakes and streams. Groundwater is a component of the hydrological cycle which tells about the occurrence of water and the processes by which it moves. Vertical distribution of groundwater. Let's talk about that. A water table is the area between the water saturated ground and unsaturated ground below which the rocks and soil are full of water. At times, below the water table are the pockets of water called aquifers. The region of subsurface from the ground surface to the water table is the unsaturated zone. It contains both air and water where the pore spaces do not fill with groundwater. The area below the earth's surface is saturated or filled with groundwater, called the saturated zone. In this zone, all of the voids are full of water. The water table marks the boundary between the saturated and unsaturated zone. It is the surface at which fluid pressure equals the atmospheric pressure. Thus, groundwater refers only to water in the saturated zone beneath the water table. The water zone beneath the earth's surface is called the subsurface water. The saturated and unsaturated zones are connected and the position of the water table fluctuates seasonally and with the effects of groundwater abstraction. The water table level is not necessarily completely level. It rises with the hills and sinks with the valleys. The water table intersects the surface in springs, rivers and lakes. There is perched water table above the actual water table if a porous and permeable rock lies above the saturated zone. You can see the figure 1. In humid regions, recharge areas through which water percolates underground are found everywhere except streams and adjacent floodplains. On the other hand, in arid regions, recharge areas encompass only the mountains and adjoining alluvial fans and the streams, below which porous alluvium soil is there through which water can percolate and recharge the groundwater. Groundwater is available at great depth in dry or arid regions, whereas it exists at shallow depth in humid areas. Seasonally, water table rises during the rainy season and sinks in the dry season. Change in climate, for example, major increases in frequency and intensity of exceptional rainfall events in groundwater recharge areas result in water tables rising to much higher levels, thus causing extensive groundwater flooding with damage to property and crops. Land use can also influence an area's water table. Most groundwater is formed from excess rainfall percolating the land surface. Urban areas often have impervious surfaces such as roads, etc. These prevent water from seeping into the ground below. Instead of entering the zone of saturation, water becomes runoff and the water table dips. Lands having irrigation from surface water source has the greatest impact on groundwater, both quantitatively and qualitatively, and excess water infiltrates into the shallow aquifers. Geology often determines the quantity of water that filters below the zone of saturation, making the water table easy to measure. Porous rocks can hold more water than dense rocks. For example, an area underlain with pumice, which is a light and porous rock, can retain a fuller aquifer, is easier to assess than the water table of an area underlain with hard granite or marble. Properties of materials. The degree to which a body of rock or sediments will function as a groundwater resource depends on many properties. The two important physical properties are porosity and hydraulic conductivity. Transmissivity is also an important concept in knowing an aquifer's ability to yield groundwater. First, porosity of the rock. It is determined by studying the shape and arrangement of soil particles. It is the amount of air space or void between soil particles. Infiltration, groundwater movement and storage occur in these spaces. The porosity of soil is the ratio of the volume of pore space in a unit of material to its total volume. The total amount of water that can be contained in the rock depends on the proportion of the gaps in a given volume of rock, and this is called as porosity of the rock. It is expressed as a decimal fraction or percentage. It is a measure of the amount of groundwater that is stored in the geological material. It can be defined mathematically by the equation N is equal to V divided by V into 100%, where N is equal to porosity, which is expressed as percentage. V small v is the volume of void space in a unit volume of geological materials, which is written as L cube, centimeter cube or meter cube. V is the unit volume of earth material including both voids and materials, read as L cube, centimeter cube or meter cube. Porosity ranges from 0 to around 60%. Porosity is dependent on the type of rock which contains the water. In other words, the porosity depends upon the spacing, pattern of cracks and fractures of the rocks. In sediments, the porosity of the rock depends on the grain size, shape of the grains and the degree of sorting and cementation. The sorting or packing arrangement is most important in these rocks. The porosity of well-rounded sorted sediments is significant as they are almost of the same size. Poorly sorted sediments generally have low porosity because the fine-grained particles tend to fill the void spaces. Well-rounded coarse-grained sediments usually have higher porosity than fine-grained sediments because the grains don't fit together well. You can see the fourth figure. Very fine-grained rocks make poor aquifers because of the surface tension which holds the water in them. Some shales can have up to 90% of the open space, which is depicted in figure number 5. Figure 4 shows the well sorted unconsolidated sedimentary, and the figure 5th shows the poorly sorted sedimentary. The porosity of sediments is affected by the shape of the grains. They can be of various shapes like rods, discs or books. The fabric or orientation of the particles, if they are not spheres, also influence porosity, as depicted in figure 6, which shows the porosity of well-rounded coarse sediments, which is more than the fine-grained sediments. Figure 7 shows the sedimentary deposits with disposition of mineral matter between grains, showing very poor porosity. The highly cemented sedimentary rocks have a lower porosity, as shown in the figure 7, as compared to the cemented void spaces. In carbonate, sedimentary rocks such as limestone, groundwater occur in fractures and cavities formed as a result of the dissolution of the sediments. This is shown in figure number 8, which shows the solution increases the porosity of the rocks. In igneous and metamorphic rocks, which are very dense crystalline rocks, porosity is controlled by cracks, fractures and faults. Structure of the rocks and its weathering are also important factors. Porosity is low as the minerals tend to be intergrown, leaving little void space. Higher fractured igneous and metamorphic rocks, however, could have a high secondary porosity. It is depicted in figure number 9, which shows the rock with porosity. It increases by fracturing. The arrangement or packing of the soil particles plays an important role in porosity. If the particles are stacked directly on top of each other, it is called as cubic packing. It has higher porosity than the particles which are laid on top of two other particles in a pyramid shape called as rhombohedral packing. The smaller particles could fill in the void spaces between the larger particles, which would result in a lower porosity. See figure 10a and 10b. Particles exist in many shapes, and these shapes are packed in a variety of ways which increase or decrease porosity. A mixture of grain sizes and shapes result in lower porosity. It is not affected by the diameter size of the grain. Porosity is the ratio of void space to total volume. A box full of ping pong balls and other of basketballs would have the same porosity as long as the packing or arrangements of the balls is same in both the cases. Porosity is classified as primary or secondary. Primary porosity is referred to the voids present in the sediment or rock which is initially formed. Secondary porosity is referred to voids formed in the rock through fracturing or weathering after it was formed. Table 1.1 shows that clays, though have the highest porosities, make poor sources of groundwater because they yield very little water. Sand and gravel, on the other hand, make excellent sources of groundwater even though they have lower porosity than clay due to the high specific yield which allows the groundwater to flow to wells. If the rocks such as limestone and basalt are well weathered and highly fractured, they make good quantities of groundwater. Specific yield is defined as the ratio of the volume of water that moves from a water-filled rock due to gravity of the total volume of rock. Mathematically, it is written as specific yield, or SY, is equal to V drained divided by V total into 100. Table 1.1, the list shown in the table represents porosity which ranges from various geological materials. Just as water clings to glass, water also sticks to soil particles due to surface tension, cohesion or adhesion, forming a thin film around a soil particle. Thus, specific yield is less than porosity. Unlike porosity, specific yield is determined by grain size. For example, if two soil have the same porosity but different grain sizes, for example clay and sand, the soil with smaller grain size will have a lower specific yield. Clay has a greater surface area than sand. Therefore, more water will remain behind clinging to the clay particle surface. This have a greater specific yield. Specific retention. The portion of groundwater that remains as a film on particles or in pore spaces is called specific retention. It increases with decreasing grain size. Specific yield and specific retention of the aquifer material together equal porosity. Table 1.2 shows that clays, though have the highest porosities, make poor sources of groundwater as they yield very little water. Sand and gravel have much lower porosity than clay, make excellent sources of groundwater. This is because of the high specific yield of sand and gravel, which allows the groundwater to flow to the wells. Table 1.2 shows the porosity in percentage of soil and rock types. In finer sediments, porosity may be low due to water that is held tightly in small pores. Effective porosity is very low in crystalline rocks that are not weathered or highly fractured. Second, permeability. While porosity tells us how much water rock or soil can retain, permeability is a measure of the capability of rock to transmit water through its pore spaces. It is the property of the soil to allow water to pass through the gaps between them. Since voids are present in all the soils, even in the most stiff soil clay, they all are permeable. It is a slow process, on an average being a few centimeters per day. Without the voids or interconnected pore spaces, the liquid or gas will not flow. The size of pore space and interconnectivity of the spaces help determine permeability. So, shape and arrangement of soil grains play the main role. The term hydraulic conductivity is used in explaining groundwater and aquifer properties. Hydraulic conductivity understands that water is the fluid moving through soil or rock type. Water can percolate between pore spaces and fractures between rocks. Larger the pore space, more permeable is the geological material. The sample size of mixed grain sizes, which is poorly sorted, has lower permeability because the smaller grains fill the openings made by the larger grains. Soil, sand and gravel are porous and permeable. Though clay and shale are porous and can hold a lot of water, the pore spaces within these fine-grained soils are small for water to flow through them very slowly. Clay has low permeability due to small grain sizes with large surface areas and less connectivity of pore spaces. Sandstone and conglomerate are highly permeable due to the presence of large interconnected pore spaces between the grains. This is depicted in table 1.3. If the permeability of the ground is uniform and there is an increasing gradient of slope of the water table, then the velocity of groundwater flow increase. This is called hydraulic gradient. Table 1.3 shows the permeability for sediments. In rocks with fractures, permeability is determined by the size of the openings, the degree of interconnectedness and the amount of open space. The movement of groundwater. The movement of groundwater is not stationary. It flows due to differences in porosity, permeability, elevation and pressure gradient through pore spaces at extremely low velocity driven by potential energy. The flow velocity of groundwater is expressed in meters per day. Groundwater permeates through the soil layers after being activated by the force of gravity. Permeability decreases downward as the excessive weight exerted by the overlying soil makes the bottom layer compact. The groundwater tends to move down the slope from water table areas of higher elevation to regions of lower elevation. Such differences of the water table are known as hydraulic head. This difference results in the movement of groundwater from recharge areas to discharge areas. Groundwater may naturally come out from the subsurface and flows in the form of a spring, stream, lake, ocean or seep, or by being transpired by plants. The rate at which groundwater flows is dependent on the hydraulic conductivity and the rate of change of hydraulic head. The difference between hydraulic heads divided by the distance between them is the hydraulic gradient. In the mid-19th century, Henry Darcy experimented on sand filters for water treatment. He measured the flow rate or discharge with units of volume of water per unit time, which is similar to stream discharge through porous medium, that is sand. He found that the amount of flow through a porous medium is directly proportional to the difference between hydraulic head values and inversely proportional to the horizontal distance between them. When combined with the hydraulic conductivity of the porous medium and the cross-sectional area through which the groundwater flows, Darcy's law states Q is equal to Ka multiplied by dH divided by dL, that is volume by time, where Q is equal to flow discharging through a porous medium, K is the hydraulic conductivity, that is length divided by time, A is the cross-sectional area, that is length square, dH is the change in hydraulic head between 2 points, that is length, and dL is the distance between 2 points, that is again length. The hydraulic conductivity is a property of the porous medium and the fluid that represents the ability of the geologic structure to transmit water. The higher the hydraulic conductivity of a medium, easier it is for the water to flow through it. This law provides the rate of volumetric flow of water. Generally, it is less than 1000 feet per year. More steep the slope of the water table, the faster the groundwater flows. In impermeable rock as the shale, groundwater flows only a few centimeters per year, while a permeable gravel, groundwater can flow large distances, say to hundreds and thousands of meters in a day. Aquifer depletion, the threats of overuse of groundwater. Groundwater is largely used by people around the world, especially where availability of surface water is not there. It is under severe crisis due to its depletion in various areas. Aquifers can be measured by water tables. They are used to extract underground water in order to meet the growing demands of the population, such as industry, agriculture, plants, etc. Pumping groundwater over the long term causes problem of some water tables dropping very quickly. This process is called aquifer depletion. Some of the adverse effects of groundwater depletion are lowering of the water table. Number 1, the excessive groundwater pumping in an area below which the ground is saturated with water has a severe consequence of the land being subsided. As water levels decline, the rate of water the well can yield may decline, hence these wells are not able to reach groundwater. Second, increased costs for the user. As the water table lowers, the water must be pumped further to reach the surface. Using more energy, this may increase the user's cost. Third, land subsidence. Land subsidence occurs when there is a lack of support below the ground. This process is mostly caused by human activities from the discharge of groundwater. When water is drawn out of the soil, it collapses, compacts and drops. Without groundwater filling pore space, the aquifer compacts and the surface of the land drops. This subsidence of land depends on factors as type of soil and rock below the surface. At times, aquifers are recharged artificially to prevent them from compacting. This recharging is done by pumping natural flood waters and treated wastewater back into the ground. Water quality deterioration. Water quality threat to groundwater reserves is contamination from salt water intrusion. Under natural circumstances, the boundary between the fresh water and salt water is relatively stable, but excessive pumping in coastal areas can cause salt water to move inland and upward, leading to salt water contamination of the groundwater. All of the water present on the ground is not fresh water. Also, most of the very deep groundwater and water below oceans is saline. The onset of the 20th century sees a threat of aquifer depletion as activities such as industry, agriculture have drained the aquifer faster than it could naturally replenish itself. Groundwater can last indefinitely only if the withdrawal rate from wells does not exceed the recharge rate. Unfortunately, this is not taking place, and many aquifers are being discharged at a faster rate than they recharge. Contamination of groundwater. Soils and rocks have a natural ability to filter impurities out of groundwater. The electrostatic charges of clay minerals attract and remove contaminant particles from groundwater. However, certain pollutants such as raw sewage, pesticides, fertilizers, and heavy metals can pose problem if they enter the groundwater. The contaminants are added by chemical storage facilities, landfills, mines, and factories. Low density contaminants float on water and occupy the upper level of an aquifer, whereas denser contaminants fall at the bottom of the aquifer. Contaminants may also dissolve in the water. Salt water intrusion, a type of natural contamination, can be a result of heavy pumping of wells near the seas and oceans. These impurities mixed with groundwater are difficult and expensive to remove. They may be removed by pumping or in certain instances given chemical treatments. So in the conclusion we can say that groundwater is the subsurface water found in pore spaces, cracks, etc. beneath the earth's surface. It makes up more than 90% of the earth's available fresh water. Water from various sources seeps down the top layer and collects above the bedrock deep down the earth. It is a finite resource and gets replenished if extraction rate exceeds recharge rate. Also, contamination of groundwater can take place. Therefore, it is important to minimize activities that can affect quality and quantity of groundwater available to humans and the environment. Thank you, friends.